Hi students, today we can discuss the chemistry chapter 2, acids, bases and salts. So in this chapter we will be talking about the properties of acids, bases and salts. Okay, it is divided into two parts. First part today we will be discussing. In the first part we have a brief idea of the acid, bases and salts. Okay, it's given acids, bases and salts are, we know, they are used in our daily life, and acids are sour in taste, whereas bases are bitter in taste. Then there are natural and synthetic acid-base indicators used to test whether the substance is acid or base. So if you want to test or to know whether a substance is acid or base, we can use the help of indicators. They are called acid-base indicators. And there are few natural indicators. Of course, there are artificial or chemical indicators also there. First, we'll talk about natural indicators. Example, they are litmus, which is taken from a plant called a lichen, then red cabbage, turmeric, hydrangea flower, petunia flower, this geranium flower, tamarind, etc. are examples of acid-base natural indicators. Okay, we'll discuss one by one. Like first one, the litmus solution. Litmus solution is taken from a plant called a lichen. This is the plant. The picture is shown here. We have two types of litmus solutions, red and blue. It's a purple dye extracted from lichen, plant under division Thallophyta. Okay. Acid changes blue litmus. If you bring blue litmus to acid like this, it's available in liquid form as well as in paper form. Okay, so the liquid form is like this, whereas the paper form is like this. So if you bring blue litmus to acid, changes to red, whereas red litmus changes to blue. Okay, so how to remember that? Acid, base, acid red, base blue, acid red, base blue. The litmus color of acid is red, whereas the litmus color of base is blue. Acid red, base blue. That is the way you can remember it. Then this is synthetic indicators. We have before that there is a turmeric it is talking about. See, when you have a stain of curry or something in your shirts, and when you apply soap, you can see that the yellow color of the stain is changing into reddish color. The reason is this turmeric is a natural indicator which turns red with the base. Soap is basic in nature. Okay, so that is how the turmeric is acting as an indicator. Now coming to the synthetic indicators, we have two indicators available in the lab, methyl orange and phenolphthalein. Methyl orange and phenolphthalein. See this is a table of acids here. Here we have a group of bases here. We'll see whether what is the color change. Okay, so here up to CH3COH, acetic acid, it is acid. Then we have the bases here. Okay, now see the color change. Acid with red litmus, no color. With blue litmus, it changes to red. That means acid red. We learned it, isn't it? Litmus paper, the color of litmus paper with the acid is red. Whereas the color of litmus paper with base is blue. Base is always blue. Litmus paper remains blue with the bases. Okay, now coming to phenolphthalein. See, phenolphthalein is colorless with all acids, colorless, whereas pink in with the methyl orange. Phenolphthalein is pink with the methyl orange. Now, phenolphthalein is pink with the bases. Methyl orange is pink with the acids. So I'll say once again, phenolphthalein is colorless with acids, whereas pink with bases. Methyl orange is pinkish red, a light orange it is. Orange or a pinkish red with the acids and yellow with the bases. Okay, so this is the summary of color change of indicators with acids and bases. Now coming to another category of indicators, they are called olfactory indicators. What are they? These are some substances whose odor changes in acidic or basic medium. For example, so what we have to keep in mind is examples for olfactory indicators. Three examples are given there: onion, clove oil, vanilla. Onion, clove oil, and vanilla are examples for olfactory indicators. And in see, here is they are saying talking about their that onion or cloth is mixed with or is making in contact with the finely chopped onions, then we'll try cleaning that or we'll apply acid and base. So when you apply base, you can see that the smell of the onion disappears, but with acid no changes occurring. That means base removes the smell of onion, whereas acid cannot. Okay. The same is the case with the vanilla essence. Base removes the smell of vanilla, whereas acid cannot remove the smell of vanilla. The same is the case with clove oil also. Clove oil's smell that can be removed by applying base, so NaOH, but it remains unchanged with the acid. Okay, so that is uh, olfactory indicators and the test results. Now, let's talk about the reaction of acids and bases with the metals. First, we'll talk about reaction of acids with metals. So, acid and metal, which we learned in the previous chapter, acid and metal, here it is showing zinc granules and dilute sulfuric acid. So, zinc granules and dilute sulfuric acid, if you mix, you can see that bubbles are coming out. Collect that gas through a bent tube, pass that gas through a soap solution taken, and let it come out and bring a burning candle near the bubble. Then we can see that the bubble catches fire and the flame of the candle goes off. Or we know the gas coming out is hydrogen, so hydrogen burns with a pop sound. Okay, so that is a test for hydrogen gas. So the result is production of hydrogen gas. So metal reacts with acids producing hydrogen gas. Of course, salt is also produced. Now, general equation is given here. Acid plus metal gives salt and hydrogen gas. So, if you repeat the experiment with hydrochloric acid, nitric acid, acetic acid, there will be variation in the speed of the or vigorous nature of the reaction. When it is coming to the acetic acid and all, which is a weak acid, the reaction is less vigorous. Okay, but the reaction products will be the same, salt and water. Equation is given here: sulfuric acid plus zinc gives zinc sulfate plus hydrogen gas. And what is the test for hydrogen gas? Hydrogen gas burns with a pop sound. We can hear that pop sound, okay, when it catches fire. Now, reaction of bases. If you allow base, for example, sodium hydroxide and zinc, you can see that they also react and forming a salt, but this salt is of a special kind. Okay, see the formula of the salt is Na2ZnO2. It is called sodium zincate, but hydrogen gas is produced very much similar to that of acids. Okay, so bases also react with the metals producing salt and hydrogen gas, but the salt is different. And one special thing is not all metals, only zinc and aluminum can react with base producing salt and hydrogen gas. Okay, So even though zinc and aluminum are producing salt and hydrogen, all other metals we cannot expect the reaction. Now the next reaction is metal carbonates and metal hydrogen carbonates. How do they react with the acids and bases? Okay, so first it is talking about acids. So he see the example here. Sodium carbonate reacts with hydrogen chloride, hydrochloric acid. Sodium bicarbonate reacting with the hydrochloric acid. Both the cases, the products are the same: salt, water, and carbon dioxide. So when a metal carbonate reacts with the metal carbonate or metal hydrogen carbonate react with acid, we are getting salt, water, and carbon dioxide. Okay, so how will you test the carbon dioxide gas? For that, what you have to do is pass the gas coming out through lime water. Okay, lime water is nothing but calcium hydroxide. So it turns milky. Why? Because it forms a white precipitate of calcium carbonate. So calcium hydroxide, which is lime water, when it gets calcium carbon dioxide, it reacts and forms a salt called the calcium carbonate in water. This calcium carbonate, what is special about? They are solid or they form a precipitate. So what happens to the solution? The solution turns milky or cloudy, we will say. Why? Because this is insoluble. But if you pass carbon dioxide in excess, if you further and keep on passing carbon dioxide to that solution, the formed calcium carbonate react to the further carbon dioxide getting to form another salt called the calcium bicarbonate or calcium hydrogen carbonate. What is special about this? This is soluble in water. So what happens? The milkiness disappears. So if you pass carbon dioxide through lime water, it turns milky first. Excess passing gives it the milkiness disappears. Okay. So this first test is used as the test for carbon dioxide gas. Okay, now how do react? That these are all examples of metal carbonates. Limestone, chalk, marble. They are all examples of metal carbonates. They are all calcium carbonate. Okay, so the general equation is given here. Metal carbonate or metal hydrogen carbonate react with acid, giving salt plus carbon dioxide and water. Okay, now how do they react to each other? How do acids and bases react to each other? Example given here, NaOH, HCl. So what happens? Salt and water. Why? And this reaction is called a neutralization reaction. You know why? Because sodium hydroxide, which is basic in nature, HCl, which is acidic in nature, both loses their property and becomes a neutral salt and water. Okay, so the reaction is called a neutralization reaction. So when an acid and base meet, what happens? Neutralization. Base plus acid, salt and water. Okay, acid base react forming salt and water. Okay, that is can be observed using methyl orange. Okay, so if you take NaOH, add a drop of not methyl orange, phenolphthalein, then the solution is becoming pink. Then keep on adding HCl and we can see that the phenolphthalein color, pink color disappears slowly and finally completely disappears. And if you add NaOH again, the color reappears like that. That experiment, that neutralization can be observed in a clear way using the help of phenolphthalein solution. Okay, now next reaction is metallic oxides with acids. So here it is showing an example, copper oxide and acid. The answer is salt and water. Metal oxide, okay? Copper oxide is a metal oxide, is still an acid. Metal oxide plus acid giving salt and water. This right part is very clear to us, or we are very familiar. Salt and water. When do we get salt and water? When base plus acid react. Okay. So when base plus acid react, we get salt and water. When metallic oxide plus acid gives also salt and water. So what is replaced? The base is replaced by metallic oxides. Okay. The base, it was base previously, now it is metallic. That means metallic oxides are also called basic oxides. Okay, because they are behaving like base, very much like a base, very much like a base they are. Okay, so metallic oxides are called basic oxides, right? Then another example, calcium hydroxide reacts with carbon dioxide. This is a non-metallic oxide, okay? So what happens when non-metallic oxide react with bases? There it was metallic oxides with acids. Here non-metallic oxide with base. Okay, there with the acid we are changing the mm, acid here. Okay, so acid, base plus acid gives salt and water. Base plus acid gives salt and water, right? So I'll replace here with the it was like this. The general equation was like this: base plus acid, right? Base plus acid as salt and plus water, right? This was a reaction. So instead of base, we have calcium hydroxide. Instead of acid, we have a carbon dioxide. So mm, carbon dioxide is a non-metallic oxide, right? So non-metallic oxide is very much like an acid. So non-metallic oxides are called acidic oxides because non-metallic oxides react with base producing salt and water, very much like a acid. Okay, so I hope it is clear why metallic oxides are called basic oxides, whereas non-metallic oxides are called acidic oxides. Okay, next is why do acids behave like this, or what is so special about, or what does all acids, what do all acids have in common? Okay, for that there is an activity given. Setup is arranged like this, in which we are changing the electrolyte with the HCl and H2SO4. If you use electrolyte diluted H2, you can see that the bulb is glowing, whereas if you use glucose and alcohol, they are also having, see, there what they are trying to say is all acids are having hydrogen gas, because we learned that acids react with metals producing hydrogen gas. So all acids are having hydrogen gas in it. But glucose have hydrogen in it, alcohol also have hydrogen in it. So hydrogen, presence of hydrogen is not the reason, no, it's not the reason why they behave like acids. Okay, that is uh, proved by this activity. So when you try the activity with HCl and H2SO4, the bulb is glowing, whereas when we try with the glucose alcohol, which is having hydrogen in it, the bulb, we cannot see the bulb glowing. Okay, so the reason, so the conclusion is uh, not because of the presence of hydrogen, it is something else. Okay, that is what we are going to discuss. So they concluded that it is not the H plus hydrogen is the reason, but hydrogen when it is in presence of water, okay, in presence of water only, it's behaving like a acid. So acids behave like acids in presence of water only. That we will prove that using an experiment. Okay, so we'll produce an acid by reacting sodium chloride and H2SO4 here. Okay, sodium chloride and H2SO4, when they react, you'll get hydrochloric acid. You'll get hydrochloric acid, but the gas hydrochloric acid produced is dry here. Okay, it is dry here. Dry hydrogen chloride is produced. So when you bring a burning, and we'll make it pure dry by passing the gas through a calcium chloride uh, block. Okay, so when you pass the gas, hydrogen chloride gas through this block, it absorbs all the moisture from it, and what is coming out will be only dry hydrogen chloride. And if you bring a dry litmus paper, the color will not change. Blue litmus paper will not change into red, whereas bring make the litmus paper wet, then we can see that the color changes to red like this. So what does it prove? It proves that acid behave like acids only when there is presence of water. So what happens with water to acid? Acid combines with or joining with water, producing a special type of ion called a H3O plus ion, which is called hydronium ion. Okay, and a Cl minus. H3O plus ions is nothing but joining of a hydrogen ion plus one molecule of water. This is how hydronium ion is formed. So you have to write either H plus aqueous or H3O plus. Okay, that is hydronium ion. So what is the reason for the acidic nature of acids? It is hydronium ion or H plus aqueous ion. Okay, now bases, what happens to bases or why bases behave like bases? That is because of the presence of OH minus aqueous ions. OH minus aqueous ions are the reason for the basic nature of all bases. Okay, in all the bases, if you observe the formula, you can see that there is presence of OH. OH will be there in all the bases. Okay, now they are corrosive. This is a symbol that shows they are corrosive. Acid in bottles containing acids and bases, we can see this emblem. Okay, now what happens to an acid or a base in water solution? It changes into hydronium ion. Okay, that we learned. In water, it forms a hydronium ion. Okay, then dilution. See that this picture shows that they are adding sulfuric acid concentrated, okay, concentrated into water. We can see that fumes are coming out. If you if you touch the surface, we can see that it's becoming very hot. The same is the case if you add sodium hydroxide pellets also to water. You can feel the heat outside. So the dissolution of acids and bases are highly exothermic. So wow, we have to be very careful while mixing acids with the water or dilution. Dilution should be done in a very careful manner and the process should be like this. See, this is the correct method of diluting an acid. What you have to do? Take water in a container, then add water of the constant sulfuric acid dropwise with the constant stirring. Or else, if you do like this, vice versa, water to acid, what happens is since it is highly exothermic, the water that is coming out is changing into vapors along with it splashes out along with the concentrated acid causing casualty. Okay, to avoid such situations, we should be diluting acids like this. Acid to water, not water to acid. This is the way to dilute acids. And again, acids are corrosive, so the symbol is used outside the bottles. And that's all for today. Thank you.